Okay, let's unpack this. Look at the room around you right now.
Yeah, just take a second to really look at it.
Right. Pay attention to like the chair you're sitting in or the floor beneath your feet, maybe the desk you are leaning against.
All that solid stuff.
Exactly. What if I told you that you aren't actually touching any of it?
It's a wild thought.
It is. In fact, what if I told you that nearly every single physical force you feel in your everyday life, the friction of your shoes, the tension of a rope, the solid ground holding you up, are basically microscopic illusions?
I mean, it sounds totally absurd when you first hear it
Right.
because we trust our senses. We trust that when we push a heavy box, the resistance we feel is just the blunt reality of two objects grinding together.
Sure, it feels completely real.
But the physical world is incredibly deceptive when you only analyze it at face value.
Yeah.
To truly understand how reality functions, we have to, well, aggressively filter out the world we see with our naked eyes.
Welcome to this deep dive. Today, we are acting as your personal guides through this really fascinating presentation deck we got our hands on.
Yeah, it's a tutorial called Decoding the Physical World.
And our mission today is to take the messy, noisy, chaotic physical reality around us and learn how to see the invisible mathematical matrix operating underneath it all.
Which sounds intimidating, but it's not.
Right, because we are going to translate all the dense physics terminology along the way. So let's start with the chaos.
Let's do it.
The presentation paints this vivid picture of a bustling warehouse. You have people pushing heavy wooden crates, someone climbing a ladder, chains swinging from the ceiling.
Just workers sweating and straining everywhere.
Exactly, a totally normal, chaotic scene.
Right, but when you look at a scene like that, your brain instantly focuses on the human element.
Yeah, the people.
Exactly. We are biologically wired to look at faces, to assess effort, to notice, like, the texture of the wooden boxes or
Yeah.
the dirt on the warehouse floor.
Which is distracting.
Very. In physics, we call all of that physical noise. It's basically sensory overload.
So it gets in the way.
Yeah. If your goal is to figure out exactly how much force is required to slide one of those massive crates, the color of the wood is totally irrelevant.
Right, or how tired the worker looks.
Exactly. The facial expression of the worker pushing it doesn't matter at all.
So we have to cut through that noise.
Mm.
The presentation introduces this concept as a three-stage architecture of simplification.
It's a great framework.
Yeah. Stage one is just observing the system, taking in that whole messy warehouse.
Just looking at the reality.
Right.
Right.
Then stage two is isolating the object. You mentally strip away the workers, the dusty floor, the swinging chains, the walls.
Just delete it all.
Exactly, until you are left with just the box floating in this empty white void.
Which brings us to the final stage, mapping external vectors.
Okay, unpack that for us.
Sure, this introduces a foundational tool called the free body diagram. We take that detailed wooden crate and reduce it down to a single, tiny, dimensionless black dot.
Just a single dot.
Just a dot, yeah, with a few arrows pointing away from it.
It's basically putting on noise-canceling headphones, but for your eyes.
Oh, I like that analogy.
Yeah, you declutter all the visual noise to isolate the one underlying signal you actually care about. Now, you mentioned vectors.
Right, vector.
A vector sounds like a villain from a sci-fi movie.
It really does.
But let's explain it simply. It's just an arrow that communicates two very specific pieces of information, right?
Yep, just two things.
It shows you a precise direction, the way the arrow is pointing, and it shows you a magnitude.
Meaning how big or strong the force is.
Exactly, which is represented by how long you draw the arrow.
And we measured the size of those arrows, like the sheer strength of that shove or pull in newtons.
Right, let's define a newton because that's the term people hear a lot.
Yeah, a newton, which is symbolized by a capital N, is the standard unit of force.
Okay.
Technically speaking, it is the amount of force required to accelerate a 1 kilogram mass by 1 meter per second every second.
That's the textbook definition.
Right, but for our purposes, just think of a newton as a standardized shove.
A standardized shove, okay.
Fun fact, the gravitational force pulling down on a medium-sized apple is roughly 1 newton.
Wait, really? Just an apple?
Just an apple.
So if I push that warehouse crate with 100 newtons of force, I'm basically applying the pushing power of 100 apples.
I mean, that's a very weird visual, but mathematically, yes, that's exactly right.
I love that.
And all of these arrows, these shoves and pulls, they interact according to the ultimate rule book of motion.
Which is?
F net equals ma. The net force equals mass times acceleration.
F equals ma.
Right. That simple equation dictates exactly how our little black dot is going to behave when we, add up every single arrow acting on it.
Okay, so we've successfully stripped away the messy warehouse. We have our single black dot floating in an empty white void.
It's a very clean workspace now.
Very clean. So let's start populating this free body diagram with the invisible forces that dictate our everyday lives.
The first one is pretty obvious.
Yeah, the very first arrow we have to draw is one we are all intimately familiar with: weight.
Right, denoted by a capital W. The presentation beautifully refers to weight as the universal downward anchor.
The universal downward anchor.
It is literally the force of gravity acting on an object's mass.
And the distinction between mass and weight here is, well, it's crucial.
Oh, absolutely. They aren't the same thing.
Right. Mass is the actual amount of stuff that makes you up. Like if you travel from the Earth to the moon, your mass doesn't change.
No, you are still made of the exact same amount of atoms.
But your weight absolutely changes because weight is highly location dependent.
Right, it depends entirely on the gravitational pull of the planet you happen to be standing on.
Okay, so when we map this onto our diagram, there is a strict geometric rule, isn't there?
There is. The origin point of the weight arrow is always drawn from the object's center of mass.
So the dead center.
Yeah, for our simplified dot, we draw the arrow starting right at the center, and it always, without exception, points strictly downward.
Downward toward the center of whatever gravitational body is pulling on it.
Exactly.
So we have our universal anchor pulling us down. But if gravity is constantly pulling our dot downward, why isn't my coffee cup plummeting toward the center of the Earth right now?
Right, it's just sitting there.
Yeah, there has to be an opposing force keeping it sitting peacefully on my desk.
And that opposing force is called the normal force, which is symbolized by a capital N.
And we need to clarify the terminology here.
Definitely, because normal in physics doesn't mean ordinary or like typical.
Right.
It actually means perpendicular. The normal force is the perpendicular force exerted by a surface pushing back against an object resting on it.
Wait, let me make sure I'm wrapping my head around this.
Okay.
Are you telling me that as my coffee cup just sits there, completely still, the wood of my desk is actively exerting energy to push up against it?
It has to. Think of the surface of your desk like an incredibly stiff trampoline.
A trampoline.
Yeah. When you place the cup on it, the microscopic bonds in the wood bend ever so slightly under the weight.
Oh, I see.
They compress. And just like a compressed spring, they push back up to regain their natural shape.
That's crazy to think about.
It is. And on a purely horizontal surface, the normal force pushes back with a magnitude perfectly equal to the object's downward weight.
But exactly opposite in direction.
Exactly. The forces cancel each other out, which is why your coffee cup doesn't fall through the floor, nor does it, launch into the ceiling.
It's just wild to realize that keeping things perfectly still requires this active, ongoing battle of forces.
Counterbalance.
Yeah. So we have the vertical axis covered, weight pulls down, normal force pushes up. But let's go back to our warehouse worker.
The guy with the crate?
Right. What happens when they lean into that heavy crate and try to slide it horizontally across the floor? They meet the resistance,
And we call that the friction force.
represented by a lowercase frif.
Right. Friction results from the physical contact between two surfaces.
Hmm.
And there is a universal directional rule for your free body diagram here, too.
Which is?
The friction arrow always strictly opposes the direction of actual or intended motion.
So if I push the box to the right, the friction arrow automatically points to the left.
Every single time.
It's the universe's ultimate contrarian. Whatever I try to do, friction points the exact opposite way.
It really is. It just resists change.
Yeah.
And, there isn't just one type of friction to overcome. There are two distinct phases.
Right, the presentation breaks this down.
Yeah, you have static friction, which applies to an object at rest, and kinetic friction, which applies to an object that is already sliding.
And the formulas the presentation gives for these rely heavily on this one symbol, the Greek letter mu.
Ah, yes, mu.
Let's explain mu simply because it looks like a weird little U with a tail.
Good idea.
It's basically just a rating of how grippy two specific surfaces are when they touch, right?
That's a perfect way to put it.
Like ice sliding on smooth steel has a very low mu rating.
Very slippery.
But thick rubber treads on rough asphalt have a very high mu rating.
Exactly. It's the coefficient of friction. You take that grippiness factor, multiply it by the normal force, which, remember, represents how hard gravity and the surface are squeezing the two objects together, and you get your total friction force.
Okay. That makes sense.
But the crucial insight here, the mathematical truth that dictates how we physically interact with the world, is that static friction is always equal to or strictly larger than kinetic friction.
Oh, this explains so much of everyday human struggle.
It really does.
The presentation gives a specific example of shoes on a wood floor.
Right.
The static mu, the grippiness when you are standing perfectly still, is zero point 0.9. But the kinetic mu, the grippiness once you are sliding, drops to 0.7.
Which means it takes significantly more force to break an object out of state of rest than it does to keep moving once it's already sliding.
This is exactly why pushing a heavy couch across the living room is so exhausting.
The worst.
You lean in, you push, your face turns red, your muscles burn, and it just doesn't budge.
Because you are fighting that massive threshold of static friction.
Right. But the second it finally gives way and starts sliding, you suddenly don't have to push nearly as hard to keep it coasting.
Because you've transitioned into kinetic friction.
That is so cool.
And on a microscopic level, when the couch is sitting still, the jagged microscopic peaks and valleys of the couch legs are like sinking into the microscopic peaks and valleys in the floor.
Like puzzle pieces.
Yeah, they're interlocked. To get it moving, you have to push hard enough to physically lift those jagged edges out of each other's grooves.
Okay, I see.
But once it's moving, they are sort of skipping across the top of one another, which offers much less resistance.
Okay, so we've pushed the box, but what if we change tactics?
How so?
What if we bring in a crane, attach a thick steel chain to the crate, and hoist it up into the air? We aren't pushing anymore,
Now we are dealing with the tension force.
denoted by a capital T.
Right. The presentation calls this the architecture of stretching thin.
Which is a cool phrase.
It is. And the word tension actually derives from the Latin word meaning exactly that, to stretch thin.
Oh, interesting.
Yeah, you observe this force anytime a load is hung using strings, ropes, cables, or chains.
And the directional rule for tension is fascinating because it's so intuitive once you think about it.
It really is.
The tension arrow always pulls away from the object, strictly along the axis of the rope.
Always.
Because you can't push a rope. If you try to push a rope toward a box, it just goes slack.
Exactly. Tension only exists as a pulling force.
So if a crate is dangling from a crane, the tension vector points straight up the chain.
Pulling away from the crate, counteracting the downward vector of the crate's weight.
So let's look at our master toolkit here. We've mapped out the physical world.
We have.
Weight is our downward anchor. Normal force pushes perpendicularly away from surfaces. Friction stubbornly opposes motion. And tension pulls away along ropes.
Our four main arrows.
Right. These four arrows dictate motion. But, and this is where the presentation pulls the rug out from under us.
The big twist.
Yeah. If we zoom in close enough, like with a powerful enough microscope, 3 of those 4 arrows are completely fake.
What's fascinating here is the stark division between macroscopic and microscopic reality.
Totally.
Because, we've built this neat, tidy, highly useful system of macroscopic arrows to help our brains predict motion.
And it works.
It does. But the presentation breaks down the microscopic origins of these forces. Weight is legitimate.
Okay, gravity is real.
Yes, weight is uniquely produced by the gravitational field pulling on mass. Gravity is a fundamental reality of the universe.
Here's where it gets really interesting. You're telling me gravity is real, but the others aren't.
Not the same way, no.
Because the material explicitly labels normal force, friction, and tension as macroscopic illusions.
They are illusions in the sense that they aren't distinct, separate fundamental forces of nature.
Okay.
They are all, at their core, the exact same phenomenon wearing different disguises. Which phenomenon?
They are strictly the result of cohesive electromagnetic forces.
Wait, let me make sure I am actually understanding the scale of this.
Sure.
You're saying that the friction of my tires on the road, the tension in a suspension bridge cable holding up thousands of cars, and the floor currently keeping my chair from plummeting to the center of the earth
Yes,
are all just tiny atoms playing tug-of-war with electromagnetic fields.
that is exactly what is happening. We call them intermolecular forces.
That is mind-blowing.
It is. Let's go back to your coffee cup sitting on the desk.
Okay.
Every atom in the bottom of that ceramic cup has a cloud of electrons buzzing around its exterior.
Right.
And every atom in the wooden desk also have a cloud of electrons. And as we know, electrons carry a negative charge.
And as anyone who has ever played with magnets knows, if you push two negative ends together, they violently repel each other.
Precisely. So as gravity tries to pull the cup down into the desk, The electron clouds of the cup come incredibly close to the electron clouds of the desk.
And they fight back. Exactly. The immense microscopic electromagnetic repulsion between those billions of negatively charged electron clouds is what pushes back against the weight.
Wow.
That invisible magnetic pushback is what we macroscopically label as the normal force.
And friction.
It's the exact same underlying mechanism. As you slide the cup sideways, the jagged atomic landscapes of the two surfaces are scraping past each other.
So they're getting close again.
Right. Atoms are coming into close proximity, electromagnetically attracting and repelling, constantly forming and breaking tiny, momentary atomic bonds.
And that collective drag,
That chaotic microscopic static, yeah, is what we feel is friction.
which means the tension in a rope.
Is just the electromagnetic bonds holding the molecules of the rope together, fiercely resisting being pulled apart.
That is wild.
When you pull a rope, you aren't feeling a single mechanical connection. You are feeling a chain reaction of billions of tiny electromagnetic magnets refusing to let go of each other.
So we just use different names, normal, friction, tension, just to make the math easier for our human brains to handle.
Yeah, on a macroscopic scale.
Yeah.
But fundamentally, all contact forces are just electromagnetism at play.
It is incredibly humbling. I mean, we take this chaotic tactile world, we simplify it into dots and arrows so we can do the math, and then we find out those arrows are basically just different flavors of electromagnetism.
It's all connected.
But, we have this toolkit now. We understand the vectors and we understand their true origins. How do we actually use this simplified matrix to solve a real world problem?
Well, we can look at the classic physics scenario provided at the end of the text.
Slide 11, right.
Imagine a block positioned at the very top of an incline, like a ramp. It starts from a dead stop and is going to slide down.
Okay, got the picture.
To make it simple, we assume the ramp is perfectly smooth, meaning zero friction.
So no energy is lost.
Right. Our task is to calculate exactly how fast that block will be moving the moment it reaches the bottom of the ramp.
Okay, a block sliding down a frictionless ramp. The text solves this using the law of conservation of mechanical energy.
It does.
Let's translate the math they show into a concept we can all visualize. Instead of reading off algebraic variables, let's think of the block's energy like two separate bank accounts.
Oh, I like that analogy.
Thanks. We have a height account representing potential energy. Because the block is high up, gravity has the potential to pull it down.
Right. The higher you go, the more funds are in the height account.
And we have a speed account representing kinetic energy. The faster the block moves, the more funds are in the speed account.
That works perfectly.
So at the very beginning of the scenario, the block is at the top of the ramp, completely at rest.
So the height account is totally maxed out.
Right. It's full of potential. But because it isn't moving at all, the speed account has a balance of absolute zero.
And as the block begins to slide down the ramp, something beautiful happens.
Because there's no friction.
Exactly. Because we've isolated our system and removed friction, no energy is lost to heat or sound. The block simply transfers funds from the height account directly into the speed account.
By the time it reaches the bottom of the ramp, the elevation is zero. So the height account is completely bankrupt.
But all that energy didn't disappear.
Right, it was perfectly transferred into the speed account. The kinetic energy is now fully maxed out.
Mathematically, the text shows this by setting the initial potential energy perfectly equal to the final kinetic energy.
Let's break those formulas down really quick.
Sure, potential energy is calculated as mass times gravity times height.
And kinetic energy.
Kinetic energy is calculated as 1/2 times mass times velocity squared.
So what does this all mean? The most striking thing happens when you look at that final balanced equation.
It really is surprising.
Yeah, you have the mass of the block on the left side of the equation and the mass of the block on the right side.
Which means
Mathematically, they cancel each other out entirely. The mass completely vanishes from the problem.
it drops out of the equation completely. If you solve for the final speed, the only variables left are gravity and the height of the ramp.
Which means the final speed of this block has absolutely nothing to do with how heavy it is.
Nothing at all.
If you took a tiny, hollow wooden block and a massive lead-filled safe, and you slid them both down a frictionless incline side by side, they would hit the exact same speed at the bottom.
Our human intuition screams that this shouldn't be true.
Right, it feels wrong.
If you watch that happen in the real world, your brain, heavily influenced by physical noise, would assume the massive safe must behave differently.
Because it looks heavier, it looks more dangerous.
Exactly. But the pure physical truth, revealed by stripping away the environment and trusting the isolated vectors, proves that mass is irrelevant to final speed in this specific system.
It is so satisfying when the math cuts through our human biases and just hands us the raw mechanics of the universe.
The beauty of physics.
We've gone on quite the journey today. We started in a messy, noisy warehouse full of heavy boxes, sweat, and physical distraction.
And we learn to mentally isolate the object.
Right, to reduce that overwhelming visual complexity down to a simple, dimensionless black dot on a free body diagram.
From there, we mapped out the invisible vectors that govern motion.
The universal downward pull of weight, the perpendicular pushback of the normal force.
The stubborn interlocking resistance of friction and the pulling architecture of tension.
And then we discovered that beneath that entire macroscopic toolkit lies an even deeper, stranger truth.
The microscopic reality.
Yeah, that while gravity is a true field force, the everyday interactions of contact, every push, every slide, every pull, are all just macroscopic illusions.
They are nothing more than invisible electromagnetic fields clashing at the atomic level.
It's a profound way to recontextualize your everyday physical struggles.
You are interacting with the fundamental forces of nature every time you take a step or move an object.
Which brings me to a final thought I want to leave you with, building right off of those microscopic origins.
Oh, I'm ready for this.
If normal force and friction are truly just electromagnetic repulsions preventing atoms from actually passing through one another,
Yeah.
if it's just negatively charged electron clouds forcefully pushing away from other negatively charged electron clouds, that means the atoms in your fingers never actually make physical contact with the atoms of the things you hold.
Never.
Because of that microscopic electromagnetic repulsion, there is always a tiny, infinitely small gap of empty space between you and the object.
Always a gap.
Which means, scientifically speaking, you have literally never physically touched anything in your entire life.
Now, that is a thought to end on.
Something to think about the next time you hold someone's hand.